I want to introduce graphs in the context of physics and point out to you the three major types of graphs that'll show up in this course, especially as relates to kinematics, which is the first topic that we're discussing. Now, there are lots of different types of graphs, but we're just going to talk about the main three, the big three that will show up over and over in discussing kinematics. Before we talk about graphs, let's talk briefly about notation. There are in math textbooks, in physics textbooks, loads of different notations that you might encounter relating to graphs. You might have seen something written in the form of, y, or you may have seen it y as a function of x, or you may have even seen the notation f of x, where, again, this is just some function of my independent variable. So if we were writing this down, we might say y equals 3x, or we could write it y of x, not y times x, but y as a function of x equals 3x, or some function of x equals 3x. You'll see all of these different notations. For my part, I will stick to this notation. It's the cleanest and simplest and tends to be the least confusing for students. So now let's talk about the three major types of graphs. These are the types that will show up in introductory physics over and over and over again. And the first type is just a constant graph. This is when I have some function that is a constant. Now, a lot of students, when they see this, they think, oh, well, that's a point in space. Well, it's not. Remember, this is y, my dependent variable, doesn't depend on x. It stays the same value for all values of x. And so if I looked at this as a graph, say c, if c is positive, then this would be my graph. It's just a straight line. This is for c being positive. If instead c were negative, of course, I would have a graph down here, maybe below the origin, for c that's negative, or c less than 0. Now there is one other special graph I want you to make note of or know about. People forget that it is a graph and that it is a constant graph, and that's the graph of y equals 0. When we have some variable equal to 0, as you might guess, it's just a straight line on the 0 axis, on the x-axis. This might show up when we're talking about constant velocities. If we had a constant velocity here that was positive, this would be the shape of the velocity versus time graph. Of course, if we had a negative velocity, then we'd have this graph here. Or this could be also the shape of a constant acceleration graph. Now, interestingly enough, if we have a constant velocity graph, then our acceleration is also a constant acceleration graph, but it's this one. So if we have constant velocity, then our acceleration equals 0. And so we have this 0 graph. So that's the constant graphs. They're fairly straightforward, very easy, very simple. The next type of graph we want to talk about is a linear graph. So this is a straight line graph. This has a form of y equals mx plus b. You've probably seen this before. And you should know that m is called the slope. This tells us how y depends on x. And b is called the intercept. B tells us where this line intercepts the y-axis. If we were to draw a picture or draw one of these graphs, it might look like this, where we have the intercept, this is B, And if m is positive, we'll have a straight line going upwards. If m were negative instead, then we would have a straight line going downwards. So this gives us m positive, and this one m negative. Of course, we could also have b be positive or negative. In this case, b is positive, but if b were negative, we might start down with an intercept down here. And then we would have m be positive, or we could have m be negative, and both of these also then are linear graphs, right? So this gives you the shape of a graph, and the function is y equals mx plus b. So how might these linear graphs appear in our kinematic equations? Well, if we look at these first two equations, both of them have a form that is y equals some constant plus m times x, where x is our time and y is either our position or our velocity, right? So if we say, take that first equation, our y is our position, our x is our time, and our intercept is our initial x position. This is x naught. And then we have our graph either up or down depending on our average velocity. Right? If our average velocity is positive, then it goes up. If our average velocity is negative, then it goes down. In that second equation, this one, now we have a slightly different form. Now, instead of being the position, x is still my time axis, but now y is my velocity. And so my intercept is going to be my initial velocity. And then depending on whether I have a positive acceleration or a negative acceleration, I'm going to have a positive line, a line going up, or I'm going to have a line going down and a straight line going down if my acceleration is negative. So you can see that these first two graphs both have this form, this linear form of y equals mx plus b. We can rearrange it, but you should still be able to see it in the graphs. The last type of graph we want to talk about is the quadratic graph, and this is also known as a parabola. That's the shape it makes. This graph has the form y equals ax squared plus bx plus c, where a, b, and c are all constants. What do they mean? Well, c, if we set x to 0, we'll find that c is where I start my graph on the y-axis. This is sort of like the intercept. If c is negative, we'd have a negative c below the origin, and if c is positive, we'd have a c, we'd start above the origin. B, this tells me whether I start going down or I start going up. So if b is negative, I start going down. If b is positive, I start out going up. And then A tells me whether I get a smiley face or a frowny face, right? If A is positive, I will get a smiley face. If A is negative, I'll get a frowny face. So if we put this all together, say C is positive, B is positive, A is positive, I would start at a positive C, I would start going up initially, and then I would get a smiling face, and that would be my graph. This is C positive, B positive, and A positive. Well, what if I have C positive, B positive, and A is negative? This would be something like what happens when we throw a ball up into the air. Well, I'd start out going up. I'd start in the positive at a point that's positive. I'd start out going up, but I'd end up with a frowning face, right? Eventually, this parabola is going to curve downwards. So that tells us how A, B, and C influence the behavior of our graph. So how might parabolas appear in our kinematic equations? Well, if we looked at this third equation, this one, we can see that it's given in the form y equals c plus bx plus ax squared, where c is my initial position, b is my initial velocity, and a is my acceleration divided by 2. So anytime we're dealing with this third equation, we already know that we're going to get a parabola as long as we have a value for C, B, and A. Let's suppose I were standing at the top of a tall building and I threw something down off the building. Now we're only dealing with one dimension, so I'm throwing it straight down. That's something to remember. So our x is time, and our y is position. Well, I start out on a tall building, and if I set the ground to be my x equals 0, then the height of that building is positive. My initial position ends up being positive. I'm throwing it down, so I'm going to start off by going down. And I know that gravity points down. So when I look at the way my graph looks like as I throw it in time, so the actual object is just going straight down like this. This is the motion diagram of the object. But as I move in time, as we said, always moves forward. This would be the shape of my graph, of my position with respect to time. And then once I hit the ground, of course, it's a little uninteresting. It just stays on the ground. But at least until we hit the ground, until right before we hit the ground, we have this parabolic shape. This is a parabola. And so we can understand how time relates to and influences these other variables by the graphs that they make. Let's finish off by looking at how the graphs of different variables, position, velocity, and acceleration, relate to each other. We're going to start with the simplest one, that's constant position. This is a position that's not changing with time at all. If my position is not changing, then the graph of that position would just be my initial position forever. It's kind of boring. My velocity graph would look something like this, where it's always 0. And my acceleration, since my velocity is never changing, also ends up being really quite boring. It's 0 forever. The second set of graphs is still pretty simple. This is for constant velocity now. So if I have a constant velocity, we would expect that my graph of velocity stays the same forever. If my velocity is never changing, then my acceleration at all times is also quite boring. It's just a straight line. It's a constant graph, but the constant is 0. The one that's a little bit interesting is the position graph. Because my position graph, if my velocity is constant, then my position changes linearly with time. If I have a positive velocity, then my slope goes up. If instead I have a negative constant velocity, so that it looks like that, then my position graph goes down. And of course, these could shift around up and down on the x-axis, but we're just talking about relative shape. The last one we'll talk about is constant acceleration. Constant acceleration comes up, as we've already discussed, when we're in free fall or when we talk about projectile motion. And so we should know what that looks like. Constant acceleration, that means the acceleration graph is quite boring. We just have some initial acceleration, whatever our acceleration is, and it stays the same forever. Just like we looked at velocity, constant velocity, and position, constant acceleration versus velocity then gives us, if our acceleration is positive, gives us a straight line going up. And if instead our acceleration is negative, then we would get a straight line going down. The position graph is the one that's really interesting. If we have a constant positive acceleration, we said that we would get a smiley face if our equation is quadratic. Well, the position graph that has an acceleration is quadratic with time. And so if my acceleration is positive, then my position graph curves upwards. If instead my acceleration is negative, then my position graph curves downwards. And so we have this relationship. If my acceleration is constant, then my velocity is linear and my position is quadratic. And again, the position of these lines may change, and their slope or their curve may change a little bit depending on our values. But I want you to understand, and here's an opportunity for you to memorize this, I want you to understand how the different graphs relate to each other, so that you know if you see a position graph that curves upwards, you know you have a positive acceleration in that portion of your graph, and you know what the velocity graph would look like for that portion. So that's our short discussion on graphs. You'll see this come up in lab, and you'll get lots of practice with it in lab, looking at different graphs, whether they're quadratic, linear, or constant. You'll also get this as you solve kinematic equations or projectile motion, and we'll talk more about it in class as well.